Today we have Professor Anselmi that will tell us everything about how to do quantum gravity with purely virtual particles. So let's welcome.
Thank you very much. So we'll talk about the quantum field theory of gravity, I call it, because first of all, it is a quantum field theory. Many proposals for quantum gravity today are not quantum field theory, or have been for a long time. And I put an article there in front because it's somehow unique and special, pretty much like the standard model versus a generic quantum field theory that you may construct. So in this talk, there will be two parts. One will be quantum field theory, how it works, and then I will move to cosmology, because it may lead to predictions that could be tested in the future. So first I will explain what the idea of purely virtual particle is. I call it also fakeon, which is a fake degree of freedom. It's a different quantization prescription. I will compare it with other possibilities to make it easier to understand what's going on in a very simple example where I will give you all details. The bubble diagram, basically. And then I will tell you how to make it work in the theory of gravity. And in the second part, I will talk about primordial cosmology. Since these ideas come from high-energy physics, because quantum field theory is equipped with very powerful constraints like locality, renormalizability, and unitarity, which are very selective and make theories very predictive. I will also rephrase cosmology in a language that I'm more familiar with, which is the high-energy physics language. So I will also rephrase inflation as a renormalization-group flow of a certain type. I will define a certain running coupling and a beta function, which will be easy, which will make it easy to compute tilts and running coefficients from spectra. And we will see the predictions for the tensor to scalar ratio, this combination R plus 8 and T, which is 0 to the lowest order, but definitely not 0. And we will see the perturbation spectrum. Okay, so first of all, what is a fakeon? It's a purely virtual particle. A particle or any quantum can be virtual or real, depending on whether it's in a superposition of states and nobody is observing it, or it's a collapse and somebody is observing it. And you cannot think of a particle as always real, let's say always classical. But people have not thought that the opposite could be possible, namely a particle that's always virtual, but can never collapse, that can never be observed, that for some reason is never made real and it always remain virtual. So this is it.
So is this concept yours, or is someone else been thinking about this?
No, I don't think there is.
So it is your original concept?
Yeah, I got to this purely virtual particle some years after the fakeon. That's an understanding of what I was doing, but at the beginning, I was not really understanding like that.
Okay.
So, but now it's much clearer, yes. So to have unitarity, you have to introduce these kind of things. You can, if you want, you can integrate them out, which I say they have to be projected away at the very end. So if you want to have something in mind to follow what I'm talking about, think of, if you're familiar with gauge theories, the Faddeev-Popov of ghosts. You need to introduce some extra degree of freedom, the ghosts. And these are very useful practically, because without them, if you fix a gauge in gauge theories, you would have to solve derivative conditions and the action would be non-local, the gauge fixed one. Feynman rules would be complicated. And to keep everything local, you do this trick. And then you project them away at the very end. So this is the key thing that has also not been thought before. Namely, I come from formal quantum field theory dealing with Batalin-Vilkovisky formalism, and all other theorems. So for me, it was kind of familiar. But I discovered that this is not a familiar thing for many people. So this is a key thing, to be able to project them away. And there is a reason why you have to introduce them and project them away, because if they are purely virtual, they are also purely quantum. Normally, we quantize things from something classical. And if we quantize, we miss everything that cannot be reached from its classical limit. So nobody thought that there could be something that is purely quantum and cannot be conceived, even thought, from a classical limit. Actually, that's not completely true, because something like that was long thought about during the decade of the S-matrix, where it was thought that you could guess the right theory from analyticity properties. Well, that was very ambitious, too much ambitious. Here, I just reach this from, by a simple, let's say, continuation beyond the standard model, just one step more than the standard model. I don't want to be too creative, because I think that being conservative is less risky than, for example, other proposals which want to turn quantum field theory down for something else like string theory, loop quantum gravity.
May I?
Yep.
So you have a collider, LEP, and LEP was running on Z resonance. Suppose you tune it a little bit off the Z resonance, you produce Z bosons, they are not on shell. So they are off shell, they are still produced. You can measure the processes. Is this what you have in mind, or is it actually different?
It's a little bit different, because if you talk about the Z and W and X, they have never been observed directly. So if they were fakeons, they cannot be by data, but if they were, those peaks that have been observed would be almost the same. The peaks, around the peaks, they would be at the same, because this fakeon simulates a physical particle in most situations. But it's when you want to detect it directly that you cannot.
But what means directly?
For example, let's say the muon, because that's easier.
Yeah.
The muon you can detect directly, or you can let it decay. Now for Z, it's very difficult because of practical reasons and for the Higgs field. But if it were not for the practical reasons, it would be the same. So to detect it directly, which would be impossible if it were fake, you would have to catch it on the fly. Boost it so that it lives long enough to make it detectable. And if it is a virtual particle, that's simply not possible because it is not in the set of final states. So the only way to detect the presence of a fake one is by indirect effects on the other processes. And in those peaks, you will find effects, little effects, for high energies, not on the peaks, very above the peaks. But you have to do precise measurements to check them indirectly.
The theory is that mathematically, I understand what you say. It is not the final state.
Exactly.
Like you say. But in practice, none of the unstable particles is in a final state, right?
Yeah. What would you say about the muon?
Oh, the muon is something in between.
Because there is this discussion about people consider theories with ghosts, and that I want to reject here. And for some reason, they say that it is fine if they decay, because then they are not in the final states. I disagree with that statement, because the muon is in the final states. So the point is that the muon is in the final states because when we do scattering, we compare minus infinity and plus infinity for the S matrix. But that's just a simplistic argument. We never wait till plus infinity or start from minus infinity. So plus infinity minus infinity means just a long time with respect to the duration of your interaction. And if you boost the muon enough, the muon will live longer than the duration of your interaction. Then you can talk about the muon in the final states. So I want to get rid of these things entirely at the fundamental level, and that is the object. But the point is that, like the Fodor-Popov ghosts, which are there, but then they are not there. The point is that there you have a principle that makes everything easier, a gauge principle, and that allows you to prove theorems to all orders. And my goal was always to do the same, so some projection without a symmetry principle. Again, this is an interpretation that I understood years later. It's not really what I wanted to do. This is what I wanted to do years and years ago, and I never succeeded when I really wanted to do it. Let's go to the prescription. First, let's mention the possible use for quantum gravity, because quantum gravity has a problem that it cannot be renormalized in a unitary way. And a simple way to make it renormalizable is by adding higher derivatives. And higher derivatives produce these kinds of propagators with higher polynomials of higher degrees in the denominators. And when you decompose them, you have at least one that's multiplied by the wrong sign. And the point is that when you try and derive or prove the unitarity equation for the S matrix, you don't find that, or here in the form of the optical theorem. Here in between, you see you can insert one, that's the identity, but you cannot prove that. You can prove a similar statement where in between you have a sum over all states, but some of them are multiplied by minus due to this minus, and some of them are multiplied by plus. And so basically you can have negative cross sections or absurd things that you can reinterpret in many ways, but they are always there, one form or the other. So the idea would be to find a way to project those away such that in a suitable subspace, which is the physical one, you have the identity, and this will be valid only in a subspace. Like in gauge theories, a subspace that does not contain the Fodor-Popov ghost and anti-ghost and the temporal and longitudinal modes of the gauge fields. So for example, this would be the simplest example extension of Einstein gravity that you can consider by means of higher derivatives. But if you quantize it as usual by means of the Flyman prescription for all the poles of the propagator, then you get Steller's theory, which means that you propagate a spin-2 ghost. And that's due to this plus I epsilon in the denominator. So you need something radically new. And now we describe some possibilities and what turns out to be the answer. So first of all, you consider a propagator, unprescribed, because I don't know what the prescription will be. Let me put both signs in front, because I want to discuss both possibilities. And Flyman tells you to put an I epsilon there. And so we have a plus minus with an I epsilon. Now, observe that this propagator has an imaginary part, and that is when the virtual particle becomes real. So the particle can be virtual and real because of this. And the imaginary part is the real particle on shell. It's the delta function on shell. In front of the delta function, you have plus if this is a physical particle. You have minus if it is a ghost. So a ghost is like a -1 particle. And that is the reason why it has a problem. So the first thing that can come to your mind to find something purely virtual is to eliminate the delta function. Because then you have something that's purely virtual. And one way is to take the difference of half the sum of Flyman and anti-Flyman. Okay, the fakeon projection has something to do with this. But if you take this literally, you will get in a lot of troubles, and we will see those troubles. But naively, it seems that it works. So that's why I put here this disclaimer: follow a certain procedure in Flyman diagrams that's in the end simpler than you think. Once you clear it of all the effort we had to make to uncover it, but it's not this propagator. So I will now compare Flyman. Oops. I will compare Flyman, this propagator, and the fakeon prescription. So Flyman is plus I epsilon. This propagator I will call Flyman-Wheeler. I don't know if you're familiar with a theory by Flyman and Wheeler who considered this combination of green functions, actually in a different form. This is equal to retarded potentials plus advanced potentials, so it violates causality. For QED, and since they considered this combination for QED, which is massless, and they violate causality everywhere, they had to recover causality, and then they developed a complicated emitter-absorber theory. That's classically only. They never intended to propose it at the quantum level, so I'm just calling it Flyman-Wheeler for give it the name. But although they didn't quantize it, a classical thing should be quantized sooner or later. So, and then we will see what the fakeon propagator is, how it is related to both actually, but it is neither of the two. And we will see it in the bubble diagram, where the virtual particles propagating in between are two Flyman particles, or one Flyman and one Flyman-Wheeler, or one Flyman and one fake. And this result will always also be the same with two fake. It will not make any difference, but this is the simplest, clearest way you can describe the basic problems. And so in some places, when you are going away from Flyman-Flyman, you will have this kind of problem, two propagators with different prescriptions, plus I epsilon and minus. This is very, very bad. And for some reason, people never tried to make this simple calculation and see how bad it is. So let's see what happens with Flyman-Flyman. Yeah, you can find the details in this paper for this part. You use Flyman parameters as usual, and so that integral, you can do easily the integral on the loop momentum, and you will get to this integral on the Flyman parameter x. And then you can study, you can do the integral explicitly, we will see it in the next slide, or you can study the analyticity properties of the amplitude without even doing the integral. Anyway, you will find this very famous picture, which is the bubble diagram. And if you complexify the external momentum P, you can just stick to the external energy P0, you will find that the amplitude is analytic everywhere apart from two branch cuts. And those two branch cuts correspond to this threshold. And that threshold has a physical meaning, because when you have a violation of analyticity or a singularity by the optical theorem, you have something going on. So basically that means that when you are above this threshold, the incoming particle, this one, can decay in the two virtual particles which become real. So those two virtual particles that are virtual because they are inside the diagram, in that particular case, can become real. They're not necessarily become real. There is a cross-section that tells you when it happens and what is the probability. And so if you want to propagate purely virtual particles, they should never be allowed to become real. Okay, so this is the first thing. You have to, you see, you have to do something radically new to make this change. And if you carry on the computation to the very end, this is the result. So it's an integral of a logarithm. So it's very simple. Although the result looks complicated, it is not complicated. Just notice a few things. You have a divergence, as usual, the logarithm, which is a local divergence, as usual. This is the usual bubble. You have verse regions here written, because there is a threshold, which is the one I told you, and there is a fake threshold, which is called pseudo-threshold, where nothing happens, but it looks like something could happen, but it doesn't. So don't worry about that. And only in correspondence of the true threshold, you have an imaginary part, which is the one that is associated with the discontinuity around the cut. And that is where the virtual particle becomes real. So to understand or recall how these thresholds appear, let me go back to the integral that here is already done. But before doing the integral, you have this integral on the loop momentum and loop energy. And if you complexify the loop energy and you draw what happens in the plane of complex loop energies, so these are real loop energies where you integrate and then you have the complex plane. What do you have? You have one propagator, and you very well know that one propagator in Flyman has two poles in these positions. You have the second propagator, which depends on the external momentum, and so its two poles can move around depending on the external energy or momentum. There is a situation where the two poles of the two propagators pinch the integration path when epsilon, the epsilon of Flyman, goes to 0. And that's where you have the violation of analyticity, and you can check that this happens for this value of p squared, which is the threshold. There is another situation where they collapse, but they don't pinch the integration path. That's the fake threshold. So it looks like there is some problem, but there is no problem because the integration path is below. And that's the pseudo threshold. And luckily, there is no problem there because you see, if there were a problem there with an imaginary part there, you would have a process that is, there's a mistake here, a process that is associated to an external particle decaying into a particle of mass m and another one of mass minus m. Or the initial energy goes into a difference of energies. That's totally absurd, right? So if you have a 1 GeV particle, it can produce a 10 GeV particle and an 11 GeV particle, or 100 GeV and 101 GeV. That's instability code. So luckily, the Flyman prescription makes this impossible. But what happens if here you conjugate one of the two propagators? If you conjugate one of the two propagators, these black poles are mirrored with respect to the real axis, and you generate precisely that thing. That's the Flyman-Wheeler, the first problem of the Flyman-Wheeler propagator. Flyman conjugate has a pinching there, and so you will find an imaginary part associated with this unphysical, absurd process. And the other one instead is fine. So you exchange the roles for threshold and pseudo-threshold. If you carry out the calculation to the very end, don't want to bother you with the details, you will find other problems. The calculation is a little bit more complicated, but anyway, the basic function is still similar structure. But notice one thing, the logarithm of the cutoff, or 1 over epsilon in dimensional regularization, now is multiplied by a non-local, not by a polynomial of the external momentum, by a non-local function. So you have counterterms that are non-local. You violate locality. You violate the locality of counterterms, because these are counterterms. You violate renormalizability. You violate stability, the thing we said before, and you violate unitarity, because if you complete the computation, you will see that the imaginary part, as predicted, is associated with the pseudo threshold, which is this U minus. U minus has the difference here. And moreover, if you compute the cross-section, which is equal to the imaginary part of the amplitude according to the optical theorem, it will be negative. Anyway, you will find, as I told you at the beginning, negative cross-sections. So you violate also unitarity. So this is a propagator that is amazingly wrong in all directions. And that means that probably if you change some key things, you can find something that's completely right. So let's see what changes in the case of the purely virtual particle, the fakeon. It's actually rather simple because you can avoid all these complexities. First of all, you start from the Euclidean version of your diagram. And that means that when you compute the amplitude away from the real axis, nothing will change. So the analytic structure will be exactly the same, because the amplitude is defined uniquely by an open set far away from the real axis. It is the same by definition. The threshold will be the same. The pseudo threshold will play no role, and you will have no problem with stability. Then you start the Wick rotation. And there are two possibilities. Either you complete the Wick rotation as Flyman tells you, the plus I epsilon is equivalent to this, which means analytically, you go from the Euclidean axis to whatever you find, and that means you go there from above and you go there from below. But if you go there from above, you will here, from above, you will have a discontinuity because there is another possibility. Well, the fakeon prescription is to average the two possibilities, just that. And this changes many, many things. It will not violate stability, it will not violate renormalizability, and it restores unitarity when you have ghosts, the would-be ghosts. Because the only thing that it changes is as follows. So let's go back to the bubble as we found in Flyman. The same formula as before. This is just the same as we had before. And as you remember, there was this imaginary part that appeared precisely because of this cut. Well, the only thing that changes when you go to Flyman fake is that you lose the imaginary part. And so the virtual particles remain virtual. You can never find them real. And if you use Flyman diagrams, the change is even simpler. You had this integral with Flyman parameters. You eliminate the I epsilon. Now the argument of the logarithm can be negative, so you square it and you divide by 1/2, and that's it. If you plot, the real part will be identical and the imaginary part will be 0, because there is no imaginary part. While in Flyman you have this contribution which starts from the threshold, and this gives the cross-section for the production of those particles. So basically, when you have a violation of analyticity, you can have an amplitude that behaves in a strange way. You can see it already from the real part that you have something going on. Well, in most cases, you know normally that there is a physical process going on, like the production of those particles. In the case of the fakeon, this is just a funny shape of an amplitude with no physical process attached. So that's why I call it fake process. So you can ask me, okay, but are there any examples of, in normal theories, standard model, 5 to the 4th, where you can have the same or something similar, namely an amplitude that violates analyticity in some places, and that violation is not associated with physical process productions of particles? Yes, this is knowledge that not many people share because it's buried in the 50s. I don't know if you have heard of anomalous thresholds. Even a triangle diagram with scalar fields or a box diagram, but not a bubble. Here you can find those things even in a bubble. Normally you can find them only starting from a triangle. There are situations where the plot you can measure at CERN, for example, will exhibit funny behaviors, and that will not be associated with a resonance or anything, just a funny behavior. Now, if you ask me, have these anomalous thresholds been tested and checked by experiments? The answer is no. They have never not been found, not because they are not there, but simply because the parameters of the standard model make it very difficult to find, and probably this kind of research is not stimulating enough to convince people to do experiments just for that, but they are there, and the experts can confirm. They are predicted by the theory. So when you have fakeons, you have many more things that are not exactly like these ones, but they are in the same category if you want. They are not that strange, not even that strange. Another thing that you may come to, you may recall, or that you may think of when you hear these things, are Livic models, because this investigation actually started from the Livic models, and the initial objective was to disprove them, because I could not believe one can make sense of higher derivatives. And Lee and Vic claimed they could make sense of higher derivative theories long ago. So that was something very suspicious to me, and but that turned out to be it turned out to be impossible to disprove them. Actually, the Livic models, I don't have time to go into details, but you can find it in these two papers. They have troubles, many troubles, formally, but you can find solutions to those problems. And that will lead to these theories, which I have already polished, and the presentation is already the simplest one, avoiding all difficulties that you find along the way from the beginning. And in the end, you find something that's very different from what Lee and Vic intended. But again, the reformulated models make sense. So there are two main differences. One is that Lee and Vic did not conceive the idea of projecting away things. And their approach was more like the one suggested by Hawking and Elkin much later, but they suggested practically at that time, the end of the 60s, which is like living with ghosts in some sense. No thanks, I don't want to live with ghosts. But there are people who want. And the other thing is that in their formulation, it looked like you needed pairs of conjugate poles. It was not enough to have poles close to the real axis. They had to have finite distances and in pairs, because only if you have pairs, they can compensate and make things as they thought they could work. But then when you do that, you will find that in gravity, if you want to generate pairs of complex conjugate poles at finite distances, you will need more higher derivatives. And then you can ask me how many more. There is any number you like. That's the answer. And so the answer is not unique in this case. And the point is that, again, you are tricked into thinking that it has to be so because you start from their approach, but then when you reformulate everything and you understand that there is something totally different behind, you realize that you don't even need that. And that's where the theory comes as a unique one, because it can be realized that that assumption was not necessary. It is still necessary to prove theorems to all orders, to take a pole in the real axis, you double it, you do everything you need with pairs, and then you prove that the limit where you collapse them back is okay. You can check these papers, but this leads in the end to the average continuation mentioned earlier, and that is something that doesn't even need this complicated construction. So the idea is to take quantum gravity as this theory, which is the only extension of quantum gravity that, like the standard model of particle physics, has a gauge coupling that's dimensionless. So it is strictly renormalizable. That's why it is unique. But instead of quantizing a la Flyman, everything a la Flyman, which gives the stellar theory, you quantize the would-be ghost as a purely virtual particle. There is one caveat. Important thing is that this action I'm writing is not the classical action. It's the classical action in the same way as a gauge-fixed classical action is a gauge-fixed action with Faddeev-Popov ghosts is a classical action. That's not a classical action. That's just the classical action you use for the Flyman rules. Okay? So in the same sense, you have to interpret this classical, so to speak, action. It's not the classical limit of quantum gravity because it is redundant. It has fake degrees of freedom inside, and those have to be projected away. Because this theory is sick as a classical theory as well. It's not just that you have ghosts and violate unitarity at the quantum level. This is a sick theory. So unless you change that too, you are in trouble. But this package that I'm talking to you about has everything built in. And once you do that, and you go to the classical limit of quantum gravity, you can do cosmology. So that's the good thing. And now we move to that. So as I told you at the beginning, since this is a purely quantum thing, you cannot conceive it classically. You cannot start from something classical and quantize it. But once you have the quantum theory, you can classicize the quantum theory and find the effects on the classical equations of motion, so the Einstein equations in this case, and cosmology. I will now give you the results for cosmology, and then I will tell you how to derive them. And then that's it. So this theory of quantum gravity has propagates what? The graviton, the inflaton, it's the usual inflaton, Starobinsky one, and the spin 2 massive degree of freedom that is now quantized as a purely virtual particle. The high energy part you can find in these two papers, but in this talk I will not spend more time on that. So you can check the bubble diagrams, the vertices, the renormalization constants, absorptive parts, and so on and so forth. Going to cosmology, you can rewrite that action in a more familiar form with a scalar and Weil squared. But remember that if you do that, and I'm going to do that, although in the first paper published with Eugenio Bianchi and Marco Piva, we studied both approaches, the completely higher derivative one and the one with the scalar, and they give the same results, so we don't need to use two now. But you have to remember that if you introduce the scalar, the potential is always this one. You cannot change the potential because otherwise the theory is not renormalizable. So this theory comes from high energy physics. I claim it is unique because of that. I cannot now change the potential to anything I like. It is the only renormalizable potential. And although the theory is not manifestly renormalizable in this form, it is because it is a change of variables with respect to this one, which is manifestly renormalizable. So here I introduce the inflaton explicitly. You could also introduce this other thing explicitly and eliminate the higher derivatives inside there. That's too complicated for cosmology. You can find in one of the papers that I mentioned here, but not these ones. That's not what I'm going to do. The Friedman equations do not change because they are Weyl invariant. And now I like to rephrase everything in the language of high energy physics, so let me introduce a coupling, which is the square root of epsilon divided by 3, probably in the usual language, but I will call it alpha. And then out of the Friedman equations, you can derive a beta function. First, you eliminate the scalar, and you have this equation. Then introduce the conformal time, and you can write an equation just for the coupling and its derivative, and that's the beta function. And you can interpret this as a beta function similar to the one of QCD. You see, the first term is minus 2 something, alpha squared. You can expand it to the order you want. You can also plot it exactly. And we will see that the spectra are renormalization-group invariant. So you can use it to express the spectra and their tilts, Rani coefficients in a very simple, efficient way. Which again, I like it because it's familiar for me from high energy physics. So if you want to check how the beta function plots, here it is. I'll show you again. It's a very complicated thing. Let me explain a little bit. So you have a perturbative region, which is the slow roll one, which is this one, where it's like QCD, literally. Then you have a fixed point. You would think it's not a fixed point because you have another 0 for the beta function, but it goes to 0 with infinite derivatives, which means that it continues, and then it does this. And in the end, it will tend to the red circle. This is just a rephrasing of the usual slow roll and reheating. Okay, so the reheating in this approach is just this funny behavior of the beta function. So it's nice because in this region, everything can be rephrased in the language of high energy physics. So you might also think that the analogy works beyond the region. I don't know if it will work close to this or even beyond that. But it could be nice to think of having a quantum field theory with a beta function like that has a crazy behavior at high energies. Because normally people tend to think that at high energies you have freedom, safety. I mean, they hope things are simple just because they would like them to be simple, but there is really no reason why they should be. And another thing that this approach allows you to do is to resum the leading logs, subleading logs, and so on and so forth into a running coupling, which is this one, because you just take the beta function and you integrate it. And what is the consequence on the spectra? That the spectrum depends on k only through the running coupling. So the spectrum, which is normally, you write it as a function of k, in the super horizon limit only, actually, only, it is a function of k through alpha. It's a function of alpha of 1 over k, which is the running coupling. And you can, if you want to match the data by Planck and the others, you can run the coupling from a pivot scale to any other scale. And the coupling in the pivot scale can be derived from the data, the amplitude, AS, and the index, NS, can derive that the coupling is like the fine structure constant of QED, numerically. It's 1 divided by 115. So the perturbative expansion is quite efficient. A comment, what do I mean by resumming leading and subleading logs, which is the renormalization group flow enhancement. If you view it as a renormalization group flow, you have this gain, that instead of expanding in powers of alpha, you can expand in powers of alpha, but keep this product of order 0 and treat it exactly. Okay, this is 1 divided by 100. But the log in the spectra of Planck is something like 10, could be. So it's good to have this quantity exactly resummed. See, this is an exact expression, and inside the running coupling to the next to leading log order, you have similar exact expressions where the product alpha log is treated exactly. Okay, these are the spectra, and this is in the last paper. I computed them to the NLL order, just to show you that this theory is computable, it's calculable and predictive. And not sure I can spend too much time on this. Let's see, 15 minutes I have, yes, okay. Just to describe the formula, and then I tell you how to derive them. So these are the spectra. As you see, they depend only on the running coupling. And all the other the coefficients are constants that depend on the masses, the two masses only. That's the only thing you have around. A curiosity is that in the case of the scalars, the effect of this spin-2 fakeon starts only at very high orders. So we do not see in the Planck data, because they measured the scalars only and they are not sufficiently precise. But if they manage to measure the tensors, not Planck but others, we will see the effect of the fakeon everywhere, because on the tensors, which means the graviton, the spectrum of the graviton, you will have in zeta, it's just a denominator, shorthand notation for an expression that depends on the mass of this fakeon. You will have an impact already to the 0th order. And let me show you what is the prediction for the tensor to scalar ratio. An important thing that I will mention in a moment, telling you how to derive the spectra, and that was shown here, is that to make the construction consistent, but the ideas come from high energy physics, but high energy physics has a weakness in this respect because it is an expansion around flat space, and you cannot do cosmology by expanding around flat space. It has to do an expansion around a curved background. And when you do that, you will discover that to make it consistent, you need this bound on the mass of the fakeon. So the mass of phi can be derived, if you want, from the data of Planck, but the mass of chi cannot. If you know that it satisfies this bound, then you can predict that the tensor to scalar ratio will be in this small window. And that means, for example, with 60 e-folds, which means alpha is equal to the thing I told you before, or something, no, close to that, probably 120, then the tensor to scalar ratio is predicted to be between 3 thousandths and 0.4 thousandths. So it will be measured in some years, and as you see, the theory is falsifiable. If it is not inside this tiny window, which is less than 1 order of magnitude, the theory is in trouble. And you don't hear very much from anybody who talks about quantum gravity that they have a falsifiable theory, because normally they have approaches that can be adapted to any measurements. So I'm betting that this is the right theory, and we will see. If you want to have a perception how what it takes to check the running, well, you can take the plot from Planck and superpose the theoretical results. The linearized one is the red line, and the running one is a little bit curvy, but not too much. It's the blue line, and so this is the zoom of that. That means that it will take a lot of precision to get there. If you want to study the difference, then the running is much more apparent, and you have this picture. In the case of tensors, you will have a region because I still do not know what the value of the mass of the fakeon is, but I know that it is in that bound. And I contact some experimentalists because in Pisa we have people who work in Lightbird. So they definitely keep telling me that they will measure the tensor to scalar ratio. They still didn't, so we are waiting for it. And that means that they get to precisions of 1 part in 1,000. So I told them, look, to check these things, we have to start to go to precisions of 1 part in 10,000. That's not reachable right now, but the people I talk to are optimistic for the future. So I hope that even if that this effort to compute things to high orders will pay off, and maybe it will be testable. So the quantities you can typically derive are the tensor to scalar ratio, the tilts, and the running coefficients. But using the renormalization-group flow I defined, they're quite straightforward because you just differentiate with respect to the coupling and you multiply it by the beta function. So you can do the result. Let me just conclude by telling you how to calculate these things, because this teaches you how to deal with fakeons fake particles in quantum mechanics, basically. Because so we take quantum gravity, we classicize it. That's what we have to do. We have to classicize it to find the right classical limit, which is not this action, as I told you, because this action has this unwanted thing around, which is still around. And how does it disappear? Classical, which is also quantum mechanics, because you know the fluctuations have to be quantized in cosmology, so it's between classical mechanics and quantum mechanics. So you do as follows. You start from the action, and you insert the metric, which is the usual unperturbed background metric, and you add. I'm doing this for the tensor because the tensors, or the graviton, I mean, not the scalar, because the scalar is more complicated conceptually, so this is easier to understand. Although it's in the end the same story. The tensors are, they give more complicated formulas, but just trivial complications, not conceptually, they are much easier. So you add the two polarizations for the graviton, choosing, for example, convenient parameterizations. This is to have a momentum along Z in Fourier transform. So this simplifies a lot. And then you rewrite this action to the quadratic order. And then you have two pieces. One is the usual thing that you get in the Starobinsky limit, which is the one where you don't have the y squared term. That's easy to deal with because this is basically almost the Mukhanov-Sasaki action and equation, and then from that to the spectrum. I'm sure that many of you know how to do what to do. So this is the key thing. It has higher derivatives, and that is the thing that you need to not get rid of, but to treat properly. First thing is to eliminate the higher derivatives, which is something you can do now. So I didn't eliminate them here because that was too much complicated, but here you can do it. So you take that Lagrangian and you add something that is 0, and you write the 0 as the square of the difference between a new field and something else. So the big U field equation will set the square to 0, and so that's why you are adding a 0, right? So you see that there is a new field here minus something that you choose to simplify things with complicated expressions. But then a lucky coincidence will show you that you can, with a change of variables, diagonalize the two degree of freedom that you will remain with, which will be capital U and capital V, in the de Sitter limit. De Sitter limit means alpha equals 0. That's where the coupling is 0. This disappears. And everything else disappears. So in the de Sitter limit, the two degrees of freedom, U and V, decouple. And one is physical because it has the correct sign in front, and the other one is the fakeon. That's the limit where you know what to do, because it's basically like expanding around flat space. And it is only because there is this factorization in that limit that I can hook the fakeon projection on the curved background to the one I already know from flat space. And then I expand perturbatively in alpha from there. So that's the key thing that was unexpected, actually, because if this didn't happen, I do not still know what to do on a generic background, because all the construction coming from high energy physics it comes from expanding around flat space. But when you have a situation like this one, where luckily you go back to flat space in some limit, basically, then you can do this. And then the fakeon projection is obtained. Forgot here a sentence. You solve the V is the fakeon field equations with the fakeon prescription, or with the classical limit of that complicated fakeon prescription inside loop diagrams. And you insert the solution back, and then you find a projected action. That's it. And here it is even simpler, because it's sufficient to insert an ansatz like this, very simple ansatz. V is a function of U, and solve it. Once you know that the solution exists and it is has certain features, find it practically is very straightforward here. Oh, there is one other thing that I forgot to mention, that is, even if this formula is complicated, you see the first line contains only U, and all the rest, if you solve this V field equation, they tell you that V is order alpha squared, and so all the rest is order alpha to the fourth, which is beyond what I will be calculating. So for what I will be calculating, the first line will be sufficient. And that means that the Mukhanov-Sasaki equation doesn't know anything about u. V doesn't know anything about V, but only u. And the reason why I have to compute the V anyway is because in the end, the spectrum is the two-point function of small u, and in small u, you have capital V. And so there are many coincidences up to the next to leading order included that allow you to go through the calculation in a very straightforward way. Although, okay, I understand that formulas appear long, but this is gravity, and in the end, they are not that complicated to deal with. So, two things. One, you need V because you want a spectrum of small u, and now you have V. But to compute the Mukhanov-Sasaki equation, you just have the first line, which is already perfect, and then you do you rewrite it with a change of variables as usual, and you will find only one new thing here. Do not know if you are familiar with this equation, but normally here you have one because it's the mass term, and it's crucial for the Bunch-Davies vacuum condition that you have to impose to find the spectra. So this is something that you can eliminate with a change of variables. No reason to worry about. With a certain change you change the conformal time in a way to make it disappear, and then the Bunch-Davies vacuum condition in the new variables is okay. Straightforward. So to recapitulate, you impose the Bunch-Davies condition in the right variables. You go to the previous ones and you find the analogs of the Bunch-Davies conditions in the previous variables, which is totally non-trivial. You solve the Mukhanov-Sasaki equation perturbatively in the running coupling. And then when you solve for V, you go back to capital U by the definition. You find the fakeon V of U by the projection. You go to small u by the diagonalization, and then you find the spectrum. That is a long way, but it is straightforward. Not now that a posteriori is understood. I don't think there is I don't think there is anything upsetting. If you want to go beyond the next to leading order, then you will find the true null localities of the fakeon projection, and they will start from there, and then I still have an idea how to do it. I'm not sure it will be experimentally pressing to do it right now, but conceptually it can be interesting. So to conclude, the constraints by high energy physics, which are locality, renormalizability, and unitarity, allow us to overcome the arbitrariness of classical theories, which is a problem, I think, at least from my perspective, for cosmology, because in cosmology you have tons of models, and I'm not sure that you can predict anything if you do not select a theory somehow. And the answer of quantum field theory is basically unique. And it has only two parameters more than Einstein gravity, which are the two masses. And cosmology can allow us to measure them and then continue and test the theory to the degree of precision we want. Other constraints are, for example, the bound on the mass of the fake, which is crucial to make the predictions quite sharp. And then you can work out the spectra and the other thing. So what is my hope? First here the game is, okay, the situation is very nice because you don't even have to suggest experiments. Cosmologists are already doing them. They are measuring the tensor to scalar ratio, for example. So the game is to beat them and anticipate what they will find by means of theory. And then hopefully suggest more experiments or go into precision things and anticipate what they will find there too. And again, the people I talk to are experimentalists, however, are kind of optimistic that in the future there will be improvements from their side too. And so let's see, maybe cosmology, primordial cosmology, will turn out to be as successful in comparing the theory and experiments as the standard model was in the past decades. I conclude here. I just mention my YouTube channel if you want to follow things. It's called Quantum Gravity Theory. And if you are interested in presentations for the public, I've given talks, but this is in Italian, also in pubs. So apparently people are very interested in hearing about these things, of course presented in a way that they can understand. And so I'll leave it there. Thank you very much.
Alex. Yeah. So you computed the spectra to third order in your parameter, your running parameter.
So the tensor spectrum is to order. The tensor spectrum is one order higher because it's nicer than the scalar spectrum, but that's only because it's special. So up to up to alpha to the fourth or alpha cube. So since alpha is 1 divided by 100, you can say that here the theoretical error is 10 to the 8, and here the theoretical error is 1 over 10 to the 6.
Okay, that's what I was asking. The tensor scalar ratio, what would be the difference between each of them? If you said they will stop at this order.
What will be the difference?
Between each order in alpha.
So when you compute the tensor to scalar ratio, a tensor to scalar ratio R is basically this thing plus 8 times the tilt. And you see in this thing you have a coincidence that makes the lowest order disappear, but that's just a coincidence. In many models it is found to be 0, but that's only because they stop at lowest order. So here the correction is up to alpha 5, and this is alpha 5 as well in NT. So when you combine them, R is determined up to alpha 5. But remember, there is an alpha squared. So R is alpha squared plus 1 plus alpha squared. So the relative error is alpha cube, not alpha 5, because there is an alpha. I think so, because the hope is that people will develop techniques to improve the measurements and make precision measurements.
Okay, because usually there is a difference between what you write alpha squared plus the next order, and then there is basically no difference between every higher order.
Because of the coefficients, you mean, that grow? Because it's an asymptotic series, asymptotic expansion typically, yeah? Here you find some examples of that, and but with an alpha coupling that's 1 divided by 100, I think there is still room for some other correction. And then there will be the loop corrections anyway, which we are neglecting. So beyond, it won't have much sense to go beyond this. But conceptually, you know, there are these challenging problems to understand. So it might also be interesting. And then, okay, even if it is an asymptotic expansion, it can still be important, because the asymptotic expansion, you never know how good it is and when it will stop to be good, right? So it depends on your coupling. And this is not the fixed epsilon. This is a running coupling. So as soon as I'm going to, as I will change k, I will be able to make it useful in other regions. But that's, of course, if you're assuming that cosmologists are so good that they can enlarge this window of values of k. And for the moment, that's hard. But, you know, some predictions can take 100 years to be tested.
So this was the attempt to see the fakeon degree of freedom. And you have to go to high energies to see the effect of it. Have you been thinking about how this can affect, I don't know, black holes or some other regime?
Yes.
Because if it is a blank scale, it's very difficult to discover such a particle, right?
Yes.
Any other possibility?
So it could be that it's since its mass is in this range, it could be infinitely heavy, even beyond the Planck scale, which will be bad because in that case it will be much, much difficult. So I still hope that we will see when they measure R where it is. It depends where it is in this vertical line. So if it is here, it's better. And if it is there, it's very bad because it will be very heavy. And on black holes, I've thought about it. I still didn't publish anything because it's more challenging. I have some things to say, but not enough to make precise statements. What's interesting is to study the effect of this projection on the black hole and how it changes the physical conditions that you have to impose to make the black hole meaningful. It's one of the things I plan to look at, but it's for the moment I don't have much to say.
What the cosmological constant now? Can you explain why it's for, or it's just the usual story that you are the unit?
So here I've turned it off because to make cosmology it's not necessary. But renormalization requires it. Yes, I forgot to mention that the theory is renormalizable with that potential as long as you add the cosmological constant. The cosmological constant has to be there. No, I have no argument to from here to tell you why it should be small, other than telling you that when you start playing these games with these masses, you are familiar with many different, so many parameters that have different orders of magnitude that you get used to something small or something big. It's not something that I find very, very upsetting. It is, if you want, I can give you a reason, but I don't think it is a compelling reason. So everything here is based on unitarity, renormalizability, and locality, and the expansion around flat space. Everything is formulated, the S matrix, scattering theory, with no cosmological constant. You do not know what an S matrix is when there is a cosmological constant. You do not know what asymptotic states are. There is simply no definition of them. And so you can see, you can say that the cosmological constant is a violation of unitarity, if you want. Probably doesn't violate unitarity. It violates the very definition. You don't even have a definition of unitarity. And people have struggled to find one with the cosmological constant and define asymptotic states and S matrices. They have never found a reasonable answer. I would suggest them to do the other way around, namely to try and prove a no-go theorem, namely prove that with a cosmological constant you cannot have a meaningful scattering theory. So there is no need why we should have a meaningful scattering theory, but if you want to have one, cosmological constant should be very small, because otherwise we would see effects here. If it is small enough, then you can use with a very high degree of approximation the ideas of a scattering theory almost cosmologically.
Okay, let's go to the very beginning. So you write Lagrange, you start, you write Lagrange, and now you tell us that now you choose which one is fakeon and which is not. And this is your choice. This is not the case with Fourier-Popov ghost, because there you choose nothing. They actually never appear, right? Whatever you do, they can never be physical particles. So in this case, you have your prescription, and you can choose whenever you apply this. Is there any better mathematics behind this to understand why some particles are, why do you have to do this?
Okay, yes.
Because if you say that I have a prescription, yes, you have a prescription. Is it fundamental?
Yeah, in this case, yes. Then we can talk about adding matter, and but in this case you don't have much choice. So this theory contains these three fields. This one necessarily has to be fake because of the minus sign in front of the.
No, you want.
No, because of the minus sign in front of the Lagrangian. If you want unitarity, it has to be fake. Otherwise, it's a ghost. But
yeah,
this.
Exactly. So there are other approaches to ghosts. Let's say some other person comes out with another explanation, then you don't have this excuse.
Yeah, if they come up with an explanation, but so far they didn't. This one is the graviton. It has necessarily to be physical.
Yeah.
You could, you cannot. So what's the catch here? The point is that I've not mentioned the fact, but I also mentioned slightly the fact that you have violations of microcausality here around. You have violations of microcausality, which, as you saw in the spectra, are well hidden and even pushed to high orders at energies larger than the mass of the fake. So if this is massless and it is fake, the graviton, then you would have violations of causality everywhere. So that's a physical statement. And another physical statement why you want this to be physical and not fake is that otherwise you do not have inflation. That would be not the inflaton, but just a fake scalar field. So for this reason, I think that in this case, you would have to make this unique choice. But when you add matter, that's the big problem of high energy physics, even before gravity. You can add any matter you want, even in the standard model. You can add any matter fields you want as long as they are sufficiently heavy to be not detectable at low energies. We do not have a reason why the gauge group should be U1 cross SU2 cross SU3, and why there isn't U37 or SU49, maybe confined, maybe there are sufficiently heavy, again, if the symmetry is broken. So as I told you at the beginning, the constraints of high energy physics are really, really powerful in some cases. The gauge interactions, basically. And in the case of Yang-Mills, only the form of the gauge interactions, because they cannot predict the gauge group. In the case of gravity, it's even better, because you don't have any choice for the gauge group. And so this is the only theory you can have. But once you start adding matter, then it's an infinite arbitrariness, basically. And to that infinite arbitrariness, I'm doubling it, because everything you add physical, now you can add fake. So, yes, in that case, we do not have any guiding principle.
There is no mathematical principle that what you are describing is phenomenology. From phenomenology, you know that if it is fakeon, then this is the fake. There is no mathematical principle which tells you what is what.
No, the mathematical principle is only works when there is something with the wrong sign, then you have no choice. When there is something with the plus sign, you have both choices unless the masses are zero. So in this case, it's unique. But that's a phenomenological reason, you can say, because it's causality. Yeah, I agree. So only this case.
Other questions? No, then let's thank the speaker again. Wait.
So if you want to go to